Hello everyone. This week we're going to do a little video on hypothesis testing. We'll cover some key help for the 4.2 MyStatLab homework, as well kind of get an understanding of what we're doing. So to kind of explain this is one of the homework problems using proportions. And the reason we know it's proportions is we're talking percentages. So two types of hypothesis testing we'll do. One's based on a proportion and one's based on the mean. So for this one, I would recommend that we use StatCrunch. So how to use StatCrunch, come over here to Question Help, and then click on StatCrunch, which will open up our little StatCrunch window. Now when you're reading the problem, we want to decide what type we're doing. Like we already said on this one, because it says in a survey 31% of respondents talk about within the pets, I believe this is too high. So we're talking about percentages, so this is a proportion problem. So I come over here and I click on Stat in StatCrunch, and I come down to proportion stats. If it was a mean problem, you would either use Z-stats or T-stats based on if you know the population standard deviation. Typically we will not, so we'll always use T-stats. Once we come in here, you hit proportion stats. We're doing one sample. And then in this case, we have with summary, which means someone's already done some of the analysis for us, so we don't have to start with raw data. If we had a data set, we would click with data. So I click on with summary, and it pops up this window. So the first thing you notice we need for proportions is number of success. So we go back to our problem here, and it says, randomly selected 150 pet owners and discovered that 42 of them spoke to their pet on the answer machine. So our success is the 42. She observed 150. So that is our total. That is our N. It's our total sample size. So the number observed will always be larger than the number of success. I bring up my StatCrunch a little bit so I can scroll. Alright, and you see hypothesis test. Just last week we did confidence intervals. You check this box. Now we just stay at hypothesis test. And this is where you have to kind of go through the problem and decide what P is. Well, in a survey, 31% of respondents stated. So that's what everyone believes, because of what the survey says, right? So think of as the null hypothesis is what the majority of everyone believes, and the alternative is what you are trying to prove. Because this is in a percentage, we have to turn it into a decimal. So I'll come here and I'll put in 0.31. Notice, StatCrunch already set your alternative to 0.31. The null and alternative always equal the same number. The reason for this is you're trying to prove if this is or this is not what the true number. And then we got to go back to the problem and find our alternative. As you can see, with alternative you can do not equal to, which is a two-tailed test, greater less than, which is a left-tailed test, and greater than, which is a right-tailed test. So in this case, she said the veterinarian believes this result is too high. So she believes the true number is actually less than 0.31 or 31%. So we'll put a less than in. All right. So a recommendation I said is you click on the p-value plot. This is not required, but it does give you a nice visual to kind of see where things lie and help you decide if you should reject or do not reject the null hypothesis. So once we have done all that, we click compute. I think this is a little bit bigger. And you see, there's our null, that P equals 31%. Our alternative, what we're trying to prove, that P is actually less than 31%. And then here is our results from all those formulas that we kind of talked about. So here is our Z-stat, which is what you could get from doing it on the table, but it calculates for us. And we could compare the Z-stat to the critical value, which is one method. However, like I said, I prefer just to do p-value because the p-value is a little more straightforward to me. Because with p-value, all we need to do is compare it to our alpha. And our alpha in this case is our level of significance is 0.1 or 10%. So is 0.21 bigger or smaller than 0.1? It's bigger. And if it is bigger than our level of significance alpha, we do not reject. If it is less than, we do reject. And the reason for this is why I like the picture. Click over here, and here is our p-value, right? If our p-value is really, really small, then we're going to be down here in the what we call the lower tail. And basically, you got to look. This is the likelihood of this event happening, and you can see we've got a decent amount of the bell curve covered. So therefore, this is likely that we could get a value that the veterinarian got. If we would have got a small p-value, it would have been way down here, which means that would have been very unlikely for us to get that result if the true proportion was 31%. And that's why we reject if our p-value is really, really small, because the p-value is a probability. And it's saying, what is the probability of getting this result based on the information you have? And if it's small, then we say, hey, that's very unlikely, so therefore we would reject. Here in this case, 21% is large, so the likelihood of us getting the results we got are basically common, so therefore we do not reject. So that's how you kind of use StatCrunch to help you see the problem, and that's why I like to see this if it's mostly covered. So we'll close this out, which brings us to the last part of the problem. Does the veterinarian have a right to be skeptical, right? No, in this case, because there was not sufficient evidence. And anytime we make a conclusion in hypothesis testing, we always go back to the alternative, what we're trying to prove. So there is not sufficient evidence to conclude the population proportion of pet owners who talk to their pets on the answer machine or telephone is less than 31%, right? We go back to our alternative. We were trying to prove this. We did not succeed, so we say there's not sufficient evidence. We never say that the null is true, right? Statisticians don't like to be wrong, so if we never confirm anything, then we're okay. So this is not sufficient evidence to conclude. Versus if we would have had a low p-value, then we would have had sufficient evidence because we would have had the analysis behind it to back us up. So I hope that helps clear up how we come to our conclusions. So now let's talk a little bit about what to do for finding critical values, specifically t's. So one of your questions is going to have you find critical values. Two ways to do this. They give you a table, and it's the t-table. And notice in the table, it's area in the right tail. So unlike the z, which was in the left, t is in the right. So how do we read this chart? Well, our top row here is our level of significance, our alphas, right? So we go to problem A here, and we say that we have an alpha of 0.1. So that means we're going to stay in this column of 0.1. And then our left-hand side, as well as our right, is our degrees of freedom. And all degrees of freedom is our sample size n minus 1. But they already gave us our degrees of freedom, so we don't have to calculate it. So all we do is we come down to 10 degrees of freedom, scroll over till we line up with our level of significance of 0.1, and our critical value is 1.372. Remember, this is only in the case if we're doing a right-tailed, which is what we're doing here. In the next problem, you see we're doing a left-tailed. Well, a t-distribution is symmetric just like the z. So all the difference is you do it the exact same way, except for when you go on left, all of these numbers become negative now. So we have a n minus 20, right, which is the sample size, but we need degrees of freedom. So 20 minus 1 is 19. Now we're in the 0.01 column. So we come over here to 0.01 and we scroll down until we get to 19, and you see it's 2.539. However, remember we're doing a left tail test, which means then our t critical value is a negative 2.539. Here's where it gets a little tricky. If you want to do a two-tail, what you have to do is you take your level significance, 0.01, and you'll divide that in half. So I'll bring up an Excel. Remember, you can just type equals in Excel to get a calculation. 0.01 divided by 2 is 0.005. So we come over to 0.0005. Our degrees of freedom is 13. And you can see our answer is 3.012. Right here, right where my mouse is. Again, now this is a two-tailed though. That is our value, but it's positive and negative because we want both sides. So our answer will be a plus minus 3.012. So that's how you get the values out of a T table. If you want to use Excel, you can use Excel as well. What you do is you type in equals, and this time we want T inverse. It's a T distribution, but we want the inverse because basically level of significance, like I said, is a probability. And so the Excel is asking for a probability. And inverse functions let us go from our probability back to a value, which is, in this case, our T crit. So we put in our probability, which is our level of significance, of 0.10. Now, Excel's a little backwards of the tables. So what you have to do in this case is you have to times it by 2 because you're only doing one tail. Basically, the Excel is built up for 2 tails. So we times it by 2 to say, hey, Excel, we want all that probability to be on one side or the other, right? So that's why we have to multiply this by 2. And then we put in our degrees of freedom, which is 10. And you see we get the exact same answer that we got in the table, 1.372. If we have to do a left-hand tail, it's still the same thing. So I'll change my percentage like it does in Part B again, of 0.01. Our degrees of freedom is 20, so remember that has to be 19. So I put in 19, and I hit enter, and I get 2.539. Remember though, we want left hand. Left-taileds are always negative, so my answer is just negative 2.539. If we want to do a two-tail, it's a little easier in Excel, unlike in the tables where you had to do it. Now in Excel, you just get rid of the times 2, and you just use the actual probability or level significance. And you can see again our n is 14, so therefore my degrees of freedom is 13. And enter, and I get the 3.012. And remember, because it is a two-tailed, it is plus or minus. Hopefully that helps explain some things. Again, please look over the announcements. I'll try to post more pictures so to get some visual aids. I know it can be tough sometimes reading the book when you're learning the material. So I'll try to pull out some key factors to give you an understanding before you kind of go to the book. The book is useful though. There's great parts of how to use technology in there. There's also good parts for you all that prefer to do a couple problems by hand that walk you through how to do it by hand. And I prefer technology because I want you to understand what the results mean and not have to spend a lot of time trying to get these formulas to calculate properly. All right, I hope everyone has a wonderful week, and I will be online if you need anything. Have a good day. Bye.